Okay, so we're going to take a look at the second part of this first example. The first example kind of sets us up. It gives us a chance to see what happens when we have a forcing function that's a trigonometric function, a periodic forcing function. But it also allows us to kind of broach an interesting topic that comes up afterwards, because that sine is really part of a larger story that we've run into before in the way of our old pal Euler. So if we want to pretend for a moment that our forcing function, or excuse me, our harmonic oscillator equation with the forcing function looks very, very similar. The left-hand side is the exact same, homogeneous. But the forcing function is now a little different, something that should look kind of familiar to us, e to the it. Well, that is definitely a complex situation, and that means that the solution, whatever I plug in for y, its derivative and its second derivative, all of this has to sum up to a complex solution. And of course, because it's a complex solution, we know that it's going to have a real part and an imaginary part. So if you imagine substituting our pretend solution into the differential equation, this thing right here, if you imagine substituting this whole thing in here and here and here, you know that it must wind up being equivalent to e to the it. And that means if we're using Herr Euler's formula on the right-hand side, that means that e to the it really can be thought of as cosine of t times I times sine t. And so that means there's a real part, the cosine part is associated with the real part, and the imaginary part. And so what we're going to do is kind of I'm going to use color coding here to, in the future, talk about the real part being in the green and the imaginary part being in this light purple here. And so there's a real part, there's an imaginary part, and they always take the form of cosine is associated with the real and sine is associated with the imaginary. And so that really allows us to consider two distinct equations. Right? So the first equation coming from this guy right here is going to be the real part's second derivative plus 3 times the real part's first derivative plus 2 times the real part must be equal to the real part of e to the it. Must be equal to just cosine t. And the same thing can be said for the imaginary. Second derivative of the imaginary part plus 3 times the first derivative of the imaginary part plus 2 times the imaginary part must be equal to the imaginary part of e to the it, or the sine part. So you can think of it broken down like it is here on the bottom. So we've got a real part, and the real part is always going to be associated with cosine. And you've got an imaginary part, and the imaginary part is always going to be associated with sine. And this actually becomes really useful for us because essentially we've got two parts of the solution. And so we can think of, I'm going to make a little note here and say, we can think of, get some space. We can think of the solution process in terms of these two parts. And choose whichever part is relevant. To our particular situation. So if we're looking at a situation that involves a cosine or a sine as a forcing function, we can pay attention to the real part and the imaginary part. Now, on the surface, this seems kind of strange, and it seems like we're making things more complicated than they need to be. And truth be told, that really is what we're doing. We're following a process that's called complexification. And so at the top of the next page, you'll see that we can always complexify, what's the fancy term for it, sine and cosine functions using Euler's formula, but we do it kind of in reverse. And if you remember, Euler's formula looks like this. And Euler's formula says if you've got alpha times e to the beta it, you can factor out that alpha, and then really the e to the beta it boils down to this right here, everything inside the brackets. There's the cosine, the real part, and then there's the sine, the imaginary part. And so the real and the imaginary parts of the complex exponential are these two guys right here. And I'm just going to stick with the color coding. We've got the real part that we've seen before, and we've got the imaginary part. So when you're faced with a forcing function that is a sine or a cosine, we can kind of turn it back into an exponential and play around in exponential land, because it might just be a little bit easier than having to do a lucky guess every time that's a sine and a cosine. So let's go back to our old pal, this equation that we've solved once before. We know what the solution is. And so what we can say here is, since the forcing function is sine, we can complexify it as an exponential. And only care about the imaginary part. And of course, it's imaginary part because it's sine. So I'm going to stick with my color coding, and sine in this case is telling us it's the imaginary part. So hang on, because it'll make sense in a second once you see kind of how this works. The first thing you need to recognize is this is really simple for us, and the beta value, the thing inside the sine, the coefficient inside the sine, is equal to 1. So this is going to be much, much simpler for us. So what we can do is we can guess that our solution is going to look something like y equals alpha e I times beta, which in this case is 1, times t, and I'm going to say in our case beta is equal to 1. And so we're going to guess a function, and we're going to call this our complexified solution. And it's going to look something like this. Some constant alpha, and notice I say constant. I don't know what kind of constant it is. It could be an imaginary constant, but we don't know, times e to the I t, because beta is equal to 1. And if that's the guess for our solution, then that means we need to know its first derivative and its second derivative. And taking the derivative works exactly with imaginary numbers. It works exactly like it would before. We just pull the I down front, and we get I alpha e to the it. And its second derivative is going to be the I comes down again and creates a negative 1, so negative alpha e to the it. And so the purpose here is we've just kind of avoided having to guess multiple terms. We just have one term. It's just one exponential. So let's see what happens. We're going to sub that in and solve for alpha. So we're going to sub it in and solve for alpha. We're going to figure out what alpha value makes this true. And so I'm going to sub it into my differential equation, my second derivative. Let me stick with my color coding here. Negative alpha e to the it plus 3 times our first derivative, which is I alpha e to the it, plus 2 times our original guess, alpha e to the it, has to all equal the right-hand side. And the right-hand side in this case is, we've complexified it, so it's equal to e to the it. Now you might say, well, wait a minute, it's just sine. Yeah, but remember, we only care about the imaginary part. So I'm going to make a little note here and say, but we only care about the imaginary part. And the good news is we're not actually going to care about it for very long because over here we've got e to the it, e to the it, e to the it, e to the it. And so in every single one of those, we can kind of factor it out. We can cancel it out because that can never equal 0. So we're never worried about dividing by 0. And that means we really have an equation that looks like this. Negative alpha plus 3i alpha plus 2 alpha equals 1. And you might be thinking, okay, great, well, we've got an I there. But we can still kind of condense and factor out. And so if I combine the 2 alpha minus alpha, it just gives me 1 alpha. And so if I factor out an alpha, it'll be alpha times 1 plus 3i equals 1. Again, I'm looking for the value of alpha that makes this true. So I'm going to divide both sides by 1 plus 3i. So alpha is going to be equal to 1 over 1 plus 3i. Unfortunately, we can't actually divide by a complex number with an imaginary part. The best we can hope for is to use complex conjugate to rewrite this. So I'm going to multiply this as 1 minus 3i over 1 minus 3i. Multiply that by the complex conjugate. This is the same thing as multiplying by 1, so it's not really changing anything. But it will get rid of it in the denominator, and we'll be left with, up top, 1 minus 3i. And in the bottom, when you multiply complex conjugates, it's just the first terms multiplied together and the second terms multiplied together. So it's 1 minus 9i squared. Now, if you're seeing ahead where we're going, 1 minus 9i squared, that's the same thing as 1 plus 9. This is the same thing as 1 minus 3i up top. 1 minus 3i over 10. And that's technically not the way we would write a complex number. A complex number has to have a real part and an imaginary part. So the last little bit of rewriting is 1/10 minus 3/10 times I. So the alpha value, the constant that makes this true, is 1/10 minus 3/10 I. So that means we have our particular solution would be this constant times e to the it, right? Taken directly from our initial guess up here. But just like our note says up here, which part of this do we really care about? Well, we only really care about the imaginary part. And only part of this is imaginary. So when I multiply this through, I get 1/10 times e to the it minus 3/10 I times e to the it. And I can use Euler's formula again to re-expand that. That's what we're going to do on the next page, the top of the next page. We got some room here. So hold on to that thought as we take a look at the top of the next page. There's a little bit of space up here. And so what we're going to do is we're going to take our particular solution and expand it. And so that means it's going to be 1/10 minus 3/10 times I times e to the it is really just cosine t plus I sine t. Thank you, Euler's formula, right? So I'm going to make a little note off to the side. We used Euler to expand e to the it. So once we've done that, now it's two binomials that we can multiply together. And so we'll have 1/10 times cosine t, and that is definitely a real part because there's nothing imaginary about it. The other real part is going to come from this negative 3/10 I times this term right here, because the I times the I is going to turn into negative 1. So this is going to be plus 3/10 times sine of t. It's positive because it's the negative times the negative 1 coming from the I squared. So this is a real part, and following our code from before, color coding, that would be the real part. But there's also an imaginary part, and that comes from the 1/10 times the I sine t. And then also from the -3/10 times cosine t. Sorry, -3/10 times I times cosine t. And so that part is what we would call the imaginary part. So color code that as well. And since we know we only care about the imaginary terms in this solution, we don't care about this. This whole thing right here is irrelevant. And it's irrelevant to us since the forcing function was sine of t. Since the forcing function was sine, we only care about the imaginary part. So I'm just going to kind of put a slash through this. Not that it equals 0, it's just we don't care about that. So our particular solution that we truly care about is coming from the imaginary part. And you might say, oh, the i's, what about the i's? Well, the I gets kind of factored out, and it's the everything else that's attached to the I where we can actually see our particular solution. So our particular solution, so the true particular solution for our forcing function is y sub p equals, and then these two terms, and I can drop the I because that's what makes them the imaginary part. 1/10 sine t minus 3/10 cosine t. And so this should look really familiar because that's exactly the particular solution that we came up with all those many pages ago, right? There's our 1/10 sine t minus 3/10 cosine t. Sure enough, that's the same thing. So what we've done is discovered a kind of a workaround so that we don't have to guess multiple terms way back here. We don't have to guess a sine term plus a cosine term. Instead, we can just guess one exponential, carry this out. We have to do a little bit of arithmetic in the complex numbers, but it's not hard arithmetic. We just need to kind of keep the bookkeeping, and by the time we get to the end, we have our particular solution in terms of the real and the imaginary parts. And so down here there's a kind of a little laundry list of step-by-step to follow. And so you'll notice in here that there's the complexified solution, A, the alpha, is going to be a complex number coefficient. The only thing that's left off from here, and I don't know why I left it off in there, but there should be a beta that's sitting inside here. Beta is the coefficient inside the sine or cosine forcing function. Right? So there should be a beta inside there. This is assuming, I guess, that beta is equal to 1. Right? And so the steps are, first solve for A. You put that into rationalized form. Specifically in this case, if you remember from our example, we had 1 over 1 plus 3i. And we rationalized that by multiplying by the complex conjugate, top and bottom. And found out that that was equal to 1/10 minus 3/10 I. Right? And then the second step was we substituted that back into our complexified solution, and we expanded it using Euler's formula in order to generate a real part and an imaginary part. And whichever one you care about based on your particular situation. Like, for example, sine has to do with the imaginary part. A sine forcing function would be the imaginary, and a cosine would be the real part. So depending on what kind of forcing function you have, you can always decide which part of your solution to pay attention to. And so down at the bottom, remember, you can always check your particular solution to be sure that it works. It's time consuming to do the check. Some of these get pretty complicated, but it definitely works. Okay, that gets us to the end of this example. And the remaining video, we're just going to take a look at one more example, actually two more examples, and see how it plays out.